Ladies and gentlemen, good morning and welcome to this fourth lecture of the short course. It will deal with the modeling strategies for seismically isolated structural systems. Actually, we will use the commercial software SAP 2000, which is a finite element model software, a commercial one. And we will see briefly the main the main elements that we will use. For sure, we will deal with the frame structures, which is actually the typology of a structural system, easy to implement, and the most common also. And we will also see how to model devices. Yesterday in the numerical laboratory, we have analyzed the real experimental behavior of all the main typologies of isolators you can find in the common practice. And today we will start analyzing the possible strategies to represent the actual hysteretic response of such devices when it is highly nonlinear and hysteretic, actually, for lead rubber bearings and curved surface sliders, and also how to implement the linearly modeled response for rubber bearings, just low damping and high damping. So before starting, since yesterday we have delivered a lot of information, I have provided in the share folder as promised the video recording for all the lectures and also the slides, the notes that we have written together, and also the spreadsheet with some data that we have computed yesterday together with the scripts in MATLAB environment. But before starting the new lecture, I just want to ask if there is any question of what we have seen yesterday, which is actually a lot. Okay, maybe you need time to also to see and to take to go back to actually to what we have done, and no problem if you will have something to ask, please ask also in the next lectures, even if it is not the previous lecture what we have discussed yesterday. And also outside the organization and the time schedule of this short course, you have to feel free to write an email to me to ask questions about what we have covered in this short course. So if there is no question, I think that we can start with this tutorial. Maybe I hope that what I'm going to present is not trivial for you. For the most part of you will be, but I think that the main topics that we will cover today are very useful, just to keep in mind the main rules that we have to observe whenever you have to model a structure within a commercial software with the finite element model strategies. So I share my screen, and we can start with the presentation. The presentation will deal with the modeling of isolated structures in SAP 2000. So you will know SAP 2000 as a finite element model software, commercial software, and there are a lot of finite element models implemented within the software. Actually, we have some examples here. We can develop models, finite element models for frame reinforced concrete structures like this one. You see that there is also the core of the building, which is actually where we have stairs and the elevator. And this portion of the building is actually made up of reinforced concrete walls, but we can also model them not with bidimensional finite elements, but with just equivalent columns, so with the frame elements. The remaining part of the structure is modeled through frame elements, and also here in the foundation, we can see that there are some reinforced concrete walls which are actually modeled with the bidimensional elements, which are actually shell elements. And here we have an example for steel structures. This is an industrial building, a one-story actually industrial building. You see that you are able to model the exact bracing and all the sections for all the beams and the columns. And then there are also restraints, external load that we will go into discuss. Actually, all these issues according to SAP 2000, so this particular software. And both of these previous two models are models of the global structure. I mean, in this case, it's just a building, and so you build up the global model, the entire model of the structure, and then you perform analysis in order to come up with internal forces. Then there are also other opportunities by using the software, which is actually the third model, which is represented by this model. And this is actually an analysis of the structural behavior of a wing column joint in a steel structure. And you see that this is a model which analyzes actually the local level of a structure, so just a joint, a beam column joint, by considering, for instance, you have steel profiles, and instead of having just a frame element for the steel profile for a beam element, you are actually modeling all the plates which compose actually the profile of the column, and also the same for the beam. And in this way, with this particular level of detail, you are also able to model in the most realistic way the connection between the beam and the column, with also some stiffening layers you see here. And so in this way, you are actually producing the most realistic model of the single connection. Yeah, the same strategy can also be applied to the whole structure. Actually, I did this for a steel frame structure last year, and actually this was exactly the same mesh I adopted approximately. I mean, the sizes of the mesh is approximately this, and but what I
using SAP.
Yeah, using SAP, what I obtained is something like millions of shell elements, and so the
how long did it take to analyze such a model which has 3D elements everywhere and millions of meshes, as you say?
Yeah, actually, this model, and also what I adopted was a model with 2D elements, because all the plates are meshed into shell elements. But yeah, the structure is three-dimensional, and I found a strategy because I had to perform actually nonlinear time history analysis, but the overall structure was linear. I mean, the time response analysis I had to perform. And I found that there was a strategy within the software, which is actually which is not the direct integration of the equations of motion, but it was the modal integration. If you try to use direct integration, and this is actually what we are going to use in the software for next week, for the model I mentioned of my model of last year of the frame steel structure, it takes maybe days and so on. But if you look at the other strategy, the modal integration, the software uses actually the model decomposition of the response, of the displacement response, and actually the overall time for the run, for a single run, was actually 1 minute. It was something surprising, because instead of days, you get exactly the same response in just 1 minute. but maybe it is just because you firstly solve the modal analysis of the structure, and so you have all the modes, the vibration modes of the overall structure. In my case, it was a steel frame, and then the software has just to compute the modal functions, which are actually numerical functions which multiply the deformed shapes of each mode, so that this is very, very faster, because it uses an already performed analysis, which is the modal one. And this is actually what I recommend you to use whenever you have a linear system, simply because you have to perform the modal analysis, and the modal analysis is linear. So we cannot use this particular strategy for our purpose, just because we will have also nonlinear links for the isolation devices. But in that case, I mean, if you want to provide a model which is very detailed, like this one we see in this slide, you said that there is also the detachment of the plate of the connection between the column and the beam and the column. So this means that between this plate and the flange of the column, you should place also the gap, some gap elements. And gap elements, obviously, even though the overall structure maybe is linear, is linearly modeled, but a gap is highly nonlinear, because you just model for a compression when the gap is closed, and then whenever it opens, there is automatically the detachment of the two surfaces, and so automatically there is no response. So this is actually nonlinear. And yeah, this was the overall strategy that I adopted last year. It is because I tried to do some simplifications. Firstly, I tried to model the frame structure just with frame elements, but then there were some particular and specific connections between elements, between beams and columns, and actually they were not common connections, so that I prefer to firstly to study a single connection, something like this, something similar, and then once I've modeled that a single portion of the structure, then I decided, okay, let's model everything. I lost my vision because there was a lot of elements, shell elements, and then the connection. I tried to model also the bolts with very short frame elements, just to provide actually the proper connection and the proper distribution of stresses. And finally, I found that the model integration was the best. Actually, yeah, I could do that just because that frame structure was a reaction structure and for testing. And whenever you have some structure that you have to use for testing on the shake table, and this should be a reaction steel structure, the overall building, the overall frame should remain within the elastic range with very small deformations. So you are fairly, your model is fair enough if you use linear elastic materials. And so these are actually the level of details that you can achieve with this software. So now let's have a look at the main steps that we have to follow whenever we have to model a structure within the software. So very brief introduction to the finite element modeling procedures. There are some input information that we will use within our models, which are actually the geometry, which seems to be the easiest, but it is a little bit tricky depending on the typology of finite element that we are going to use, depending if they are frame. So we have to use the actual centroidal line of a given frame rather than shells like the model I mentioned. So you have to model the actual flange and the web for a given profile, and so on. Then materials. We have also to model materials with respect to what is provided by the code, and with respect to what is provided also from the capacity of the software. the external loads, which represent actually a very important aspect, because according to the external load, the application of them to all the elements, we will compute the internal forces for the elements, according to which we will check and design some internal portions of the structure. And obviously, we have also to define restraints. So the degrees of freedom at certain locations where we can set equal to 0 some degrees of freedom, which could be translations or rotation or both together. And actually, the modeling of a given structure is performed through a specific scheme. So this means this is an example which is shown in the slide. You can see that this is just a single story and single span frame, a plan one. You can see that this is the plan view of the lateral plan view of the frame. And according to this geometry, we have to switch to the bold geometry, which is actually the model, the finite element model geometry. And it is directly associated to the typology of the finite element that we are going to adopt, simply because we are going to consider and to use frame elements, and frame elements are defined according to the centroidal line. So this means that we have just to draw lines which are centroidal with respect to the section we are designing, and we have to remember that these line has actually a lot of informations within all the points of the line, which are actually the cross section and all the material properties and all the sectional properties. But what we are just considering just a line. And then we have to keep in mind one important concept about finite element modeling, which is actually the following. We are going also to use SUB 2000, and we will draw actually our geometry and our structure. So we will also be able to observe some extrude view of the overall structure, so that also frame elements become three-dimensional. Just because you will see the extrude view provides actually the three-dimensional view of each frame element. So you will not see just the centroidal line, but you will see the centroidal line together with the cross section for all the sections. And so your structure actually becomes alive with the three-dimensional development. But what we have to keep in mind is that we are using a software which implements actually the finite element models. And finite element models are just based on actually equations which are lumped at the nodes. Okay, this is very important, because we have to keep in mind that we look at geometry and something geometrical because we look at a three-dimensional model within a software, which is very useful because actually we can see what we are modeling, the actual connection between the elements, and also the frame elements is actually represented by a single line. But even though this is a line, we have to keep in mind that the formulation and the expressions for the finite element, the frame finite element, is just lumped. All the information are lumped within the two nodes. Okay, and the only way that we have in order for two frame elements to be really connected and to share information is just to have one of the two nodes in common and connected. Otherwise, there is no connection between the two, and so there is no sharing of information, of internal forces, of compatibility and displacements and deformations and rotations. And this implies that if we have a multi-story building, we cannot model a single frame element for the whole column for all the stories, but we have to interrupt the frame element at each story level. And this means that at the location of each story, we will have the effective connection between the beam joint and also the top joint of the previous story and the bottom joint of the subsequent story. Okay, so let's keep in mind that the whole information is lumped at all the joints, just structural joints. What we see within the software is just a graphical representation, which help us actually to provide and to see if we are doing right or not. But actually, we have to keep in mind that the real aspects and modeling strategies are lumped within the equation inside the structural joints. So very few instructions for the new model. Before, this is important whenever we use a software like SAP 2000, which is an American software. And in the United States, for instance, you know that metrical and force units are completely different with respect to the European one. And we will use to consider kilonewtons for forces and meters for generally geometry and lengths. They are different for United States. They generally use kips for forces and inches for lengths. And what happens is that since this is an American software, in some versions, as you open the software, and this is the main, the first frame that you get, the first window that you get, you have here in this corner, you have just this selection of the units. So you can select actually different combinations of units. And okay, here I just see there is kilonewton meters, so it is already what we are going to use. So there is nothing to do. But in many cases, as you open the software, you see that there are United States units rather than other typologies of units. What I suggest you to always do is to change the units before creating a new model. Okay, simply because if you change it properly at the beginning before creating the new model, what happens is that you create a model then with the proper units, and then you save your model. Whenever you will reopen your model, your structural model, the units will be set again back to what you have assumed before creating the model. If you don't do this, it is highly probable that whenever you maybe keep the US units, for instance, then you create the model and then you change the units afterward. Okay. What happens is that you save the model, you close it, and then maybe after 2 days you reopen your model. And what happens generally, it is highly probable that the units will be set again to the United States ones. Okay. And so you will notice that, and you can change it again. Okay, you will have to change units every time you will open the new model. Okay. It happens that, and it surely happens that there is the day you will not remember to change units. So what happens is that maybe you spend hours to if the structure is very large, to assign external loads to frame elements rather than combination and so on. But you are actually introducing numbers with the actually units, which are not the ones that you assumed in design and generally in the structural analysis. So what you find are actually unmatched results with respect to what you are expecting. Okay, so it is important to change units before creating the new model, so that there is no doubt. So for the definition of the new model, then after having changed the units, there are 2 steps which can be alternatively chosen. The first is which is very simple, to use the wizard of SAP 2000. There is this window which allows you to consider different fast choices. And you see there is there is the blank model with anything inside. There is the grid, a continuous beam, a 2D truss, a 3D truss, 2D frame, 3D frame, wall, flat slab. They are very similar, but this is a wall, so in the plane X, Z, and this is a flat slab, so this means that the plane is X, Y. Then there are shells, staircases, and these are tanks, and this is underground concrete, so the 3D elements, solid models, and so on. Okay. Otherwise, you see that you can change here units, but if you change it the units here and you have not changed before, then whenever you reopen your model, you will have to change again. You have to change units back to what you have guessed at the beginning. There is another opportunity within the software, which is actually to create a new model according to an AutoCAD DXF file to be imported. Okay, so it is very useful whenever you have a very large structure to model, and maybe also three-dimensional with the regular geometry, and this is very helpful just because in SAP 2000 you cannot draw exactly like in the easy way we do in AutoCAD. So we have actually to create a grid and then to modify coordinates and then to join one by one grid points. In SAP 2000 you can just connect grid points. You cannot just go from one point to a certain length of a given angle. It is quite different with respect to AutoCAD. So it is better to, if everything is very regular, to draw in AutoCAD with an in DXF file and then to import that within the software. Just pay attention about this. I just give you some suggestions for this particular point for you to do correctly. So the AutoCAD DXF has to be actually defined according to some characteristics, and the characteristics should be related to the geometrical definition of the model. First of all, we have to remember not to draw the first element once we have just opened AutoCAD, but we have to be sure that we start drawing our model when at the origin of the reference system. Otherwise, if you just open AutoCAD and you start drawing, actually the coordinates of AutoCAD, because also AutoCAD has the reference system, will be actually the same also in SAP 2000, and actually there could be some numerical problem. So first of all, in AutoCAD DXF, you have to remind to start drawing at the origin. Of the reference system. Okay. Then this is very important, and then this one, the following is just a suggestion because there are also opportunities to change a reference system, but I guess that it is better to draw immediately as we are expecting to consider our structure. So this means that you have to draw the structure exactly with the same orientation of the reference system that we will have also in SAP 2000. So let's consider the same reference system between the two softwares. So consider the same reference system between let's say SAP 2000 and AutoCAD. I mentioned AutoCAD, but you can consider whatever software is able to reproduce vectorial drawings. And then you have to draw your structure. So draw the structure in 3 dimensions. Okay, so exactly in 3 dimensions as you are expecting to have your building modeled. So beams will be along both X and Y directions, and columns will be along the Z direction. And that there will be also another issue, but we will discuss it later on in the slides. And then we have to save as the XF file. Remember to go to the options and change digits, limit digits. Because the DXF file are just numerical files with all the information of the coordinates for each point. And this means that the numerical information could have many digits, okay, for all the coordinates. Even though maybe you are drawing fixed values, I mean integer values for lengths. So maybe you have 3 meters, 4 meters. But then in the CAD environment, you may have some connection, some wrong connections. So you will not have 3.0, but you will have 2.9995. And these are actually, which can provide actually misalignments with all the elements implemented within the model. So just limit to 4. Let's consider 4 digits, which means that the precision of the detailing of your drawing will be about 1/10 of a millimeter, since we are using meters. So this, I think, it is enough for a frame structure. And I think that this is everything. Once again, okay, you have to save as a DXF file by limiting the digits, and also by providing at the end a plan horizontal view. This is strange, but this is an easiest way to not to have mistakes in the importation process of the file. So these are very easy rules to consider, and then obviously the elements. But we will see later on what I mean with which kind of elements we have to use in the CAD environment to represent finite elements in SAP 2000. So if we use the grid only wizard fast assumption, this is the most common, simply because we create the grid, and if we have a grid within SAP 2000, we have grid points, and with the grid points we are able to draw actually elements directly in SAP 2000, so we don't need to go through the definition of a DXF file in CAD environment. And this is the window for the definition, for the quick grid lines definition. You can choose both the Cartesian and the cylindrical coordinates. Cylindrical are very useful whenever you have to consider maybe tanks, which have actually a cylindrical cross, generally development, geometrical development. but we will use Cartesian. And there are actually three specifications to set. The first is the number of grid lines according to all directions. So the number of grid lines for X and Y directions, which are the horizontal ones, are directly related to the number of spans plus 1. Okay, so or in other words, we have the number of grid lines are directly equal generally to the number of columns. Okay, and for Z direction, we have the number of grid lines in the Z direction, which is equal to the number of stories plus 1, which is actually the number of stories plus the foundation level. And then the second characteristics are grid spacing, which means something like related to the span length. Okay, for the X and Y, and then interstory height for the Z direction. And remember, if you see, there is no specification for all the space that we have between all the subsequent grid lines. So this means that this particular tool in SAP 2000 just allows you to create regular grids. Okay, so with the regular grid spacing, okay, you can vary the grid spacing among the directions. So you can have a certain grid spacing for the X direction, a different grid spacing for the Y, and a different again for the Z direction. But what I meant is that you cannot have different span length for just the X direction. You can just, for instance, with the 6, this means that all these spans will be equal to 6 meters along the X direction. Maybe for Y we can have 5, but this means that for the whole Y direction we will have just 5 meters length. Okay. And this is actually what does not happen in reality, and especially in practical applications. So there is obviously the strategy to change the coordinates for all the grid lines, but it cannot be done directly here. So the main strategy by using this fast tool to create the grid is just to use it to just create the proper number of grid lines, which is directly related to the number of columns, and then just to provide a spacing which is constant, and then to go back to the definition of the grid within the software, and then to change the single coordinates of all the grid lines. This is possible, and this can be done actually afterwards, this window. Okay. So let's just consider a grid with a constant spacing for all the directions, and then we will change it according to the proper geometrical definition of our structure. And then there is the last one, which is the first grid line location, and generally you see that it is related to the origin of the reference system. So nothing different. We can actually keep it like that. Even though it is possible to change it, and you can change it in the case you want to maybe to compute the overturning moment at the base of a building induced by the seismic action. So this could be very useful for us to consider the axial load variation due to the overturning effect of the inertia forces at all the story levels. So this means that the overturning moment should be computed according to the reference, the origin of the reference system located exactly at the centroid of the plan view of the building. So this means that if you have to change the first grid line location in order to have then the origin exactly in the middle of the building. Okay, so in that case, it is possible for the software to compute the right then correct the correct value of the overturning moment. And then this is the result. You can see that we have a grid which is actually with the constant spacing. These are 6 meters. These are 6 meters as well. And these are 3 meters. Okay. So if we have maybe actually along the x direction, maybe we have 6 meters, 5 meters, and 4 meters. This is the only way to use that fast toolbox. And then we have to change the coordinates. We will see together that once we have created this draft, let's say, of the grid, we have to right-click at a certain location, at a given location of the white screen, whatever point is okay. And then there is edit grid data, and then a new window opens in order to modify actually the coordinates for all the grid lines. So we will see together when we will use the software. And this, what I mentioned before about the drawing aspects of the SAP 2000 is that you mandatorily need the grid in order to draw frame elements and generally finite elements. So this means that only if you have grid elements, you can just click on this tool and then to draw from one point to another in order to draw actually a frame element. If you don't have a grid, you cannot do that. Okay, so it is mandatory to define the grid if we want to draw within the software, the SAP 2000 software. Otherwise, the other strategy was to fully draw within the CAD environment and then to import the TXF file. Then we have for frame structures the internal forces side convention, and the reference internal forces are the following. You surely know the axial force, and then we have two values of shear force about the plane 1, 2 and the plane 1, 3. Then there is the torque moment about the axis 1, bending moment M2 and M3, about axis 2 and about axis 3. And actually, we have to keep in mind that the there are also the local axes for a given frame element, and we will see actually later on how they are defined. You see that since the torque moment is the torsional moment is about the axis 1, we can understand that the axis 1 is parallel with respect to the axis of the element. So this is the axis of the element. And the check for all the internal axes is very important because we will have to consider actually the proper definition of internal forces among and the sharing of all the information among all the frame elements implemented in the structure. So we will see later on how they are defined and how to consider and how to correct if they are wrong. So what about materials? SAP 2000, for what we are going to use it, will implement linear elastic isotropic homogeneous materials. So this means that we have just 4 important properties, mechanical properties, which are Young's modulus, which is E, the Poisson modulus, and the shear modulus G, and what is generally called gamma, which is the weight per unit volume. And you see that this is the an example of a window of the software which leads to the definition of a given material. There are a number of materials which are defined according to different standard codes worldwide. But generally, since this is just a linear elastic isotropic homogeneous material, we can just define them in the easiest way just by guessing these 4 parameters. Generally, in SAP 2000, there are some libraries of given materials according to the standard codes. because there are also some tools implemented within the software for section checks, and so see a section design for reinforced concrete and also for steel structures. Since we are not going to use them, we can just set a linear elastic isotropic homogeneous material with just these four mechanical properties. There are also some, some tools to define nonlinear materials, and I actually used them for definition also the material of a frame structure, the steel frame structure that I mentioned before. But in that case, obviously, I wasn't able to perform the model integration simply because the model was no longer linear. And what I was able to do is just to perform was just a pushover analysis because it was quite faster than days, but it kept something like half a day just for a pushover with I think 10 steps to achieve the maximum displacement allowance of the frame. So there are also issues for nonlinear materials, but they are actually time consuming. And this is for the definition of cross section. There are some classifications for sections. So if you choose concrete, the software will show the typical sections that are adopted, which are adopted for concrete elements, and the same for steel. What I just want to highlight is that if you select steel and then you select rectangular, and then within the rectangular you set reinforced concrete material and the sizes which are related to a column, for instance, in reinforced concrete, this doesn't mean that the overall section will be in steel. This is just a classification, okay? It is a classification for the shape of the most common shapes of cross sections adopted for a given material, but this is not the final material of the section. So this means that I can choose this rectangular section, which is listed among the steel sections, and then to consider it exactly like a reinforced concrete one, because the material will be set afterwards. Okay. And this is actually what I mean. This is the window where we have to set the main characteristics of the section, okay, the name of the section, and this is the easiest section, the rectangular one. We have the depth and the width, and then here we have to set the material, and here you have the list, and actually, if you have previously defined a material, a new material according to your characteristics, you will find it here. You can also add a new material here, and this tool directly access to the definition of materials that we have seen before. Then there is another important, okay, section properties provides actually a window which lists the main properties of the section, which is the area, the cross-sectional area, the moments of inertia, the shear areas, and so on, the radius, gyration radii, and so on. I just remind that the frame elements implemented in SAP 2000, it is defined according to the Timoshenko theory. So this means that the actual deformation with respect to shear forces is modeled. So it is not, we don't have to consider the Bernoulli formulation where the shear stiffness tends to infinite, so we don't account for the shear deformation. But we have to keep in mind that SAP 2000 allows for the most general formulation, so according also to the Timoshenko theory and the effective stiffness and deformation for shear forces. So this is the reason why generally when we try to compare results and computations, I mean, with what is returned by the software, maybe there is some mismatching. but actually because generally end computations are related to the Bernoulli formulation for beams, which neglect actually the deformation with respect to shear. On the other hand, the sub 2000 allows to consider also that issue with the Timoshenko theory. So this is the most general beam elements which can be considered, and in order for you to consider maybe a comparison with end computations, okay, you should be able to consider Bernoulli theory within the software sub 2000, and it is possible somehow. And to do so, we have to consider property modifiers. And with property modifiers, we obtain this window. And you see, this windows provides actually allows you to select and to set a multiplication factor for all the properties of the section. Sorry. And according to this, sorry, I just exit my, okay. According to this, we can try to model the Bernoulli theory by amplifying a lot the moment of inertia along about both the axes 2 and 3. Okay, so here instead of 1, we just set 1 to the 4th, 1 by 10 to the 4th, so 10,000 and 10,000 here. So this means that we are modeling a Timoshenko beam, but with a very amplified moment of inertia. Sorry, not moment of inertia, the shear area. The moment of inertia is actually what we are going to model. The shear area 10 to the 4th, 10 to the 4th. So we are amplifying the shear area. So automatically we can say that the shear stiffness is approximately infinite, and this is approximately equivalent to the Bernoulli theory. So we are able to compare end computations to the results of this model. Okay, so maybe here these two. For the Bernoulli theory, we set the modifiers for shear areas to 10 to the 4th. Otherwise, we have the Timoshenko theory. Then, very easy rules, but which are fundamental for the proper definition of the overall model. The drawing procedure for frame elements. This means that the elements must be drawn in the same direction of the axis of the reference system, which means that the columns should be drawn from the bottom to the top. And for instance, beams along the X direction should be drawn from left to right. Okay. And what is very important is that you will have to keep in mind to draw similar frame elements in exactly the same way. Okay, this means that all the columns should be drawn with respect to the same direction. So if you draw the first column from the bottom to the top, which is the most correct one, you will have to consider exactly the same procedure for all the columns within your model, and the same for the beams along the X direction, and the same for the beams along the Y direction. For whatever is inclined, you have to, okay, the most important thing is that if you have inclined members or elements, you have to consider just a drawing convention, let's say, and then to keep it constant with all the inclined members which are parallel or similar. Okay, this issue is directly related to the local axis of the frame elements, because in order to have the proper definition of internal forces when we have run the analysis, we should provide all these similar elements to have the same definition of local axis. Similar elements means all the columns, all the beams along the x direction, and all the beams along the y direction. And these are the local axes. They are based on a color-based distinction. The first axis is the red one, and as I mentioned before, the first axis, the first local axis, corresponds to the axis of the frame element. And you see here that the red is always parallel with respect to the frame element, the corresponding frame element. And then the other local axes are obtained by considering the three-dimensional reference system. The white axis is the second, and the blue axis is the third. The most important thing and aspect is that all the X beams must have this orientation of local axis. Just in that case, which is the correct one, we will have the proper sharing of information among all the frame elements, and then we will have the proper definition of the finite diagrams for internal forces. Then another issue which is very important is the definition of restraints, which are actually degrees of freedom which are directly set to 0 at certain locations of the structure in order to have the proper definition of restraints. And this is the overall window that is opened when you ask SAP 2000 to define restraints for a given selection of nodes. And you have to just highlight degrees of freedom which have to be set to 0. And firstly, you have to select the nodes which are related to restraints of your structure, and then you have to directly set the proper definition of restraints. You see that here you have a checkbox for all the degrees of freedom. We are in the 3D space, so this means that we have 6 degrees of freedom for each node, which are related to the 3 translations and the 3 rotation about all the 3 axes. And you can restrain all of them, which is just a fully fixed end, rather than just fix the translational degrees of freedom, which is a hinge. And then we can have the roller just by restraining the vertical translation. And actually, you can both choose here the degrees of freedom to restrain. Otherwise, you have here some fast restraints with obviously the fully fixed end, the hinge, the roller, and this is the free hand, okay, with no restraints. If you click here, automatically you have the right choice of the checkbox related to the degrees of freedom which have to be restrained. Okay, so you have, if you just need to consider fully fixed ends because you are at the base of a reinforced concrete structure, you just press here, and automatically you will have checked all the degrees of freedom, both the translations and the rotations. Then important aspect is the application of the external loads. Here there are load patterns. The load patterns are the typology of the name of loads, and there is a very important aspect to consider. We have already seen the definition of material for SAP 2000, and one of the parameters for the homogeneous material was the weight per unit volume. Okay, so you see that here the first load pattern is dead. Okay, and okay, there is type dead, and then there is a self-weight multiplier 1. So this means generally dead is the standard already defined for all the new models. And then you can decide to keep it or rather than to erase it. But generally, whenever you define a new model, you will have the dead load. And what is important to notice is that within that load pattern, SAP 2000 automatically computes the self-weight of all the structural elements which are implemented in your model according to the material that we have defined. So according to the weight per unit volume that we have defined. So it takes actually the weight per unit volume, it multiplies that value by the area of the cross section, and then you get exactly kilonewtons over meter, which is a distributed load which is applied toward the gravity direction. And if you have obviously a beam, you have so horizontal line, you have actually an external load, actually the self weight of the beam, which is orthogonal with respect to the axis. So this leads to shear and bending moment. But if we consider columns, this distributed load is perfectly aligned with respect to the axis of the element. So this means that we will have a distributed load with respect to the axial behavior of the beam element. I mean, of the frame element. So that will imply just the variation of the axial load without any shear and without any bending moment. With inclined elements, obviously we have a combination of the two. We will have a component which will be orthogonal with respect to the axis. So we will have bending moment and shear. And we will have also another component which will be parallel with respect to the axis of the element. So we will have also variation of the axial load. This is done actually by the software. So the automatic computation of the self-weight of all the elements is done within the dead load pattern, simply because there is this parameter set to 1. Okay, because there is a self-weight multiplier set to 1. So you automatically understand that it is important for this parameter to be 1 just for the dead load pattern, and then to set it to 0 for all the other load patterns that we will have for our structure. Because otherwise you keep accounting for the self-weight of all the elements for all the load patterns that we will have. So this means that here you see we have G1K, which are generally about the Italian standard code. These are permanent loads for structural elements. G2K are permanent loads for non-structural elements. UK are live loads, and so on. We will have also wind action, the snow, maybe we have a seismic action, but seismic action actually would not be actually the pattern unless we have to perform a linear elastic analysis, but linear static analysis, I mean. But generally, whenever you create a new load pattern, we have to keep in mind to set the self-weight multiplier equal to 0. Otherwise, you keep considering the self-weight and you keep adding the self-weight of all the structural elements to the overall building. And so this means that you are accounting for the gravity loads just for the frame elements that we have implemented many times, and this is obviously incorrect. And you should find these in your results. You should find a huge value of moment, bending moment and shear. And generally something unexpected with respect to what you are guessing for the internal forces to be according maybe to end computations and so on. So remember that the self-weight multiplier has to be set to 0 for all the load patterns which are not dead. Okay, and to help you to remind this, there is also this type of load pattern, simply because this type, if you set dead as type, this automatically implies that the self-weight multiplier is 1, but whenever you choose live, you automatically obtain 0. So the software automatically sets 0 for the self-weight multiplier. Okay, so just check that for all the load pattern that you are going to create here, just to choose the type of the load pattern live, and then just check at the end that you have just 0 for all the load pattern, but the dead. This is important. Everything works like what I've just described, obviously, if you have defined the self-weight per unit volume different than 0. There are some strategies for modeling according to which you may choose to set the weight per unit volume of the material equal to 0, just because you want to consider directly, manually, I would say, the dead load for all the elements. That is a choice, that is a strategy of modeling. It is up to you to decide, but I think that since there is the opportunity for the software to consider the dead automatically, so the self weight of all the elements, let's do it like this, and then at least there is no assignment of loads, at least for the self weight of all the frames. According to all the external loads that we have defined, there are also load combinations to define, and it is possible to define combinations for all the load patterns that we have defined according and in agreement to a given standard code for structural analysis, depending on the nation of the country where you are designing. And it is important whenever you have to superpose all the effects of different external load to consider load combination type as linear head. This is a linear superposition of the effects. Okay, so it is just a summation of all the effects of given load patterns. And here you have to list all the load patterns rather than also combinations with the to be summed up with okay, here there is the load case type, linear static generally, but we can consider also response spectrum whenever we have to apply a response spectrum for linear dynamic analysis, rather than maybe we have also the effects of a time history analysis, and we can add also this. And there is also scale factor. This is important whenever we have to perform some combinations for different limit states according to the standard code. For the ultimate limit states for gravity loads, for instance, we know that we should amplify loads, gravity loads. For instance, we know 1.3 times the permanent loads, the permanent structural loads, plus 1.5 times the permanent loads of non-structural elements, and then plus 1.5 for times the live loads. My guess is that it's better to define and to assign to the frame elements values of loads related to the scale factor is equal to 1, and then to rule the scale factor within the combination. Okay, I think this is the easiest way to work. And then there is also, you see, it is possible to compute a final envelope of all the combinations and configurations for design purposes, which means that instead of linear head as a load combination time, we will choose envelope. Okay, so envelope just graphically superpose all the load case, all the load cases and the load combination that we will list here. The linear superposition, the linear head, actually it sums up all the contributions. And now let's start by looking at the modeling strategies for isolation devices. So now we have seen from the theory, and also we have considered some experimental real data for full-scale devices, for rubber bearings, lead rubber bearings, and the curved surface sliders. So we perfectly know the overall response of such devices, and we expect actually a given behavior also within our commercial software. So actually, we hope that we are able to develop some models which are representative of what happens in reality. So we hope that there is some modeling strategies for them. Let's start from rubber bearings. So for both the low damping rubber bearings and high damping rubber bearings, we know that they are the easiest devices to be modeled, because they can be modeled as linear springs with respect to all the displacements, both the axial and the shear directions. And with the constant damping, since the shear strain is greater than 100%. Okay, let's keep in mind that damping and the shear modulus also for the rubber compound, these two values could be considered as constant values if the shear strain is at least 100%. And this is generally what happens in design. We assume 100% of shear strain. And we can use generally isolation devices will be modeled through link support elements. So they are something like linear, lines, so something like frames, but they are defined as links, and they have proper properties, specific properties according to the typologies that we set. So for rubber bearings, we can choose linear, which is the easiest. And actually, for all the elements, all the link elements, we have to choose the direction, which is related to the degrees of freedom, the three translations, and the three rotation. Remember that the link works exactly like a frame elements in terms of local axis. So this means that the first direction you want is the axial one, whereas the U2, which is related to the shear direction along the x axis, whereas the U3 is the shear direction along the y axis. Okay, and we don't look at the rotational degrees of freedom simply because we just need to consider the translational ones. Okay.
Sorry, can I ask something?
Yeah.
In the description, you say that the rubber bearing can be modeled as a linear spring.
Yeah.
But actually, you're opening the window of links,
yes.
right?
Yes.
Are they the same in terms of the definitions of SAP 2000 or not?
You mean that there is a link with the rubber bearing, right?
Yeah. So this is what I didn't really get. So you're gonna model the isolation devices as spring,
yeah,
and connect them with the structure using a rigid link, or I misunderstood something.
No, a rigid link actually cannot be used simply because actually it is not actually the behavior that we are going to model. They are the links that we are going to use are related to linear the linear typology by choosing the proper value of stiffness. I don't know if I'm mismatching the meaning of the question.
But it's simply like when you say in SAP link, does it mean spring?
Yeah,
Okay.
It is a link is it could be fixed. It could be a rigid link also. Yeah, if you assume the typology of link linear, and then you select all the degrees of freedom and then you fix them, this is a rigid link. Okay. But
perfect.
if you don't fix the degrees of freedom, they are free, and you can associate it together according to this option and then to this window, the stiffness coefficients and the damping coefficients for all the degrees of freedom.
Perfect. Thank you.
Yeah, this is important whenever you have you need actually the a rigid link. Rigid links are useful in many times. For instance, when we have to model the core of a building for staircases and elevators, we have to join the equivalent columns of the reinforced concrete walls with the rigid links, and that could be the case. You see also here, you just check fixed and you are fixing degrees of freedom. In our cases, since we need to model the linear behavior of such devices, you see there are stiffness values and damping values. You can choose actually if you need a stiffness which is uncoupled rather than stiffness coupled. And stiffness uncoupled means that you will set just a single value per direction. Okay, you will have just a single value for U1, single value for U2, and single value for U3, and this is actually what we are going to use, and the same for damping. Stiffness coupled, these 6 components become actually a matrix of 6 by 6, simply because the software is expected to have a component also for related combinations of degrees of freedom. So you will have also a stiffness value for U2 with respect to U1, U3 with respect to U1, and so on. This is not actually what we are going to model, simply because for rubber bearings we use generally a very simple very simple definition, which is just a spring, a linear spring with respect to displacements, and independently X and Y and Z, and this actually leads to fairly good results in comparison to what happens in reality. And the value of U2 and U3, which are the one related to the shear directions, we know that this is GA over H isolation, whereas the U1, okay, this can be set as a high value. It could be also defined according to the theory, but we will see how to define this value. But yeah, if you define just a very high value, not too high in order not to have unconvergence of the solution of the problem, but I think that if you set something like 10 to the 5th, you are properly modeling the vertical direction of the isolation. And regarding damping, okay, we don't consider any damping for the vertical direction. We should consider damping for the shear direction. Okay. And remember that here you don't need damping in terms of damping ratios. Okay, you don't have to set, maybe you are designing a rubber bearing with the 10% target equivalent viscous damping, but those values should not be equal to 10%, which is the damping ratio, but they should be equal to the damping coefficient. Okay, and the damping coefficient, which is called what we generally call C within the theory of the single degree of freedom oscillator, this is equal to 2 damping ratio omega and the mass. Okay, so this means that whenever you design actually a structural system, you have maybe, and we will see tomorrow how to design the fast design rules. We have a design period value for the isolation system. If we have this, we have also a design value for the angular frequency, which is 2 pi over period. And we can use this value of omega isolation here. For the mass, we consider the whole mass which is above the isolation layer. So what we have called in previous lectures m tot, so the total mass.
So it's not the damping ratio what we have to input, it's the damping constant C, right?
Yeah, exactly. So okay, we consider constant damping ratio, which implies also constant damping coefficient. Yeah, and to consider the damping coefficient, yeah, we assume that the design period, which in other words is also represented by the design angular frequency, is the one which rules the damping within our analysis. And the damping, this is, let's call it CD, which means damping ratio design, which is actually the design value that we assume at the beginning of the overall application. What we find with this expression is the global damping factor, the damping coefficient, the global damping coefficient related to the whole isolation system. Since we are setting the properties for the single isolator, we have to consider the number of isolation devices. So the values that we have to consider here is actually C, which is defined as the global damping coefficient divided by, which is equally smeared among all the implemented isolators. Okay, so this is a very fast way to compute the actual damping coefficient for the linear. This is something like a linear dashpot, what we have called linear dashpot in the previous lectures. And the C value is defined according to the equivalent viscous damping ratio, which is assumed in design at the beginning of the design, the total mass, which is above the isolation layer, and the total number of isolation devices. And I just remind that the total number of isolation devices when we use rubber bearings, it is not necessarily equal to the total number of supports numbers. Okay, because we will surely have hybrid systems, so combinations of rubber bearings and flat sliders. Is there questions about that? Okay.
She has the best.
There is someone with the open microphone.
It's me, sorry.
Yeah, okay. Then let's switch from the lead rubber bearings. For lead rubber bearings, we know that the overall constitutive law is actually non-linear, and it is hysteretic. So there is actually a typology, which is a rubber isolator. And this rubber isolator is actually a typology of link, which is highly nonlinear because it is elastoplastic response with the hardening corresponding to the response of the rubber compound. And again, for the vertical direction, we can just set a high value of stiffness. So we can linearly model the isolation device for the vertical direction, which is U1. Remember that we have local axis exactly like frame elements. So the one direction is related to the axis of the link. Whereas for the shear directions for U2 and U3, we have this definition. You see that there is always the distinction between the property used for linear analysis cases, but we will deal with non-linear analysis cases. Sorry. Okay. And you see that the main parameters for non-linear analysis are stiffness, yield strength, and the post-yield stiffness ratio, which means that we have the hysteretic force response, and then we have something like this. So what is asked by the program is the initial stiffness, which is K. This let's call it this K2. This is let's say Fy, and so the stiffness is K. The yield strength is Fy, and the post-yield stiffness ratio is K2 over K. Okay, once we set actually these mechanical properties, we have exactly the hysteretic behavior for lead rubber bearings. Finally, curved surface sliders, there is an actual typology of link, which is friction isolator. And again, for the first direction, which is the vertical direction for the link, this could be linearly modeled according to a very high value of stiffness, and the shear behavior according to the translational degrees of freedom U2 and U3. There is actually a model implemented in the software, which represents the frictional response. So this theoretical frictional response, together with the recentering behavior as an additional linear response with respect to the displacements. So these are the properties used for nonlinear analysis cases. You see that there is again a stiffness, and then there is friction coefficient, slow, fast, a rate parameter, and the radius of sliding surface. Okay. Let's consider this stiffness simply because we know that the overall frictional response is something rigid and then plastic. But something rigid cannot be modeled through the software. So what the software does is actually to consider the rigid branch of the frictional response like an elastic branch. So what we have to guess is an initial stiffness which is high enough to fairly reproduce the frictional response, because we know that we have seen also yesterday from the experimental point of view, and we know also from theory, that the unloading and the loading branches for the cycles of the response of curved surface sliders are fairly vertical, which means a rigid constitutive law. In order to do this, just not to try just numbers, high numbers to represent that stiffness, we can guess numerically that stiffness by considering the effective value of frictional force, so friction coefficients times the applied vertical load to the device, divided by a sort of rigid displacement, which is a fairly small displacement, which could could be considered between 0.5 and 1.5 millimeters. I would say that generally, for what I have observed in my computations, that displacements lower than 1 millimeters could lead to never-ending analysis. So you will not achieve convergence at a certain point of the analysis. So maybe one rather than 1.5 millimeters. Could be good, and actually if you consider 1.5 millimeters with respect to maybe the design displacement, which could be also to 200 millimeters or also higher, this is a very small portion of that. So I think that they could be considered as a vertical branch, even though you consider a finite value of stiffness. And then you see there is a friction coefficient, slow and fast, and rate parameter, and these are related to one of the common dependency of the friction coefficient, which is with respect to the velocity. And we have observed this dependency yesterday, and actually one general dependency is to consider, according also to one of the previous research works of Professor Michael Costantino, we can consider the friction coefficient as exponentially increasing for the first values of sliding velocity, and then a constant value is achieved asymptotically. And according to our experimental results and our investigations, generally this value of velocity afterwards, we can consider a constant value of friction coefficient is something like 50 millimeters per second. And the rate parameter is something related to this number, which is actually, this should be 1 over 0.05. Okay, It is actually the inverse of the velocity. It could be estimated through the inverse of the velocity. After that, we have a constant value of friction coefficient. Generally, that dependence, okay, that is the, I think, the dependency of the friction coefficient on a response parameter, which causes the most negligible influence in the overall response of the structure. Because there is another very important issue, another very important dependency of the friction coefficient, which is the one related to the applied vertical load. We have seen yesterday the huge decrease in trend, exponential decrease in trend of the friction coefficient with respect to the applied load. And that is much more significant with respect to the slight dependency and the slight increasing trend of the friction coefficient with respect to the sliding velocity. And actually, the portion of the increasing branch for this dependency is so small, and for so low values of sliding velocities that the shape of the overall hysteretic loops is much more comparable to the purely rectangular one. So this means that this dependency could be neglected. So what you can do is just to consider the friction coefficients low and fast equal to the same value. So the design one, and whatever is the rate parameter, once you set these two values equal, this doesn't have any influence. The radius of sliding surface is the equivalent radius of curvature, and it is measured according to the units that you have set at the beginning of your model. So since we have chosen meters, we have maybe 3 meters if we have to model the device that we have considered yesterday, and we will have a numerical value returned by the design procedure. And this is a very important issue. We have to keep in mind that this particular link, so the friction isolator, this one, allows the software and allows the model to consider the lateral force response of the isolator as a direct function of the applied vertical load. So the force is actually a function, the lateral force, the horizontal force is actually a function of the applied vertical load. So this means that W, as the vertical load applied to that location, may have different influences. For instance, there will be also the fluctuations induced by the overturning effect induced by the inertia forces at all the levels of the structure. But we can also have, if we want to consider also the vertical component of the seismic event, there will be also the variation of the axial load induced by the vertical component. And actually, all these issues will be modeled within and will be considered as additional influences and additional variation also in the horizontal response. This has to be kept in mind because there is another strategy to model such isolators, and generally there are some softwares which don't have actually this friction isolator, but just have, for instance, the rubber isolator, which provides an elastoplastic with hardening hysteretic rule. And one of the softwares is Seismostruct, for instance. For what I know, there is no friction isolator, but there is a definition of friction, but actually there is no variation of the horizontal response with respect to the applied vertical load, but you can just define an initial strength, so a yielding point, and then the post-yield stiffness, but the horizontal response is not a function of the applied force. The applied vertical force, I mean. So you can exactly define the same theoretical hysteretic loop, but you have to keep in mind that these modeling strategies does not account for the dependency of the lateral response with respect to the applied vertical load. So, okay, these This is not so high if you just consider the overturning effect of the inertial forces, and you don't consider a significant vertical component of the seismic event. But generally, you have to at least to remember that your results will be affected, slightly affected from that. And then finally, the typology of the analysis.
Sorry, Professor.
Yes.
I have a very simple question.
Yeah.
What you can say more about the location of the shear deformation? What's the effect on the analysis?
What do you mean the location with the location?
Where there is the parameter shear deformation location distance from NJ.
Oh yeah, that could be set to 0 because this is not actually a parameter which influences the overall response of the bearing, and this could be considered also. Yeah.
I'm sorry, but what's the meaning? I mean, there is an effect on the P delta effect, something like this. What's the meaning of this?
Actually, I have never used that parameter, but I think that there could be also something related to second order deformations, which can be also checked within the help actually of the software. But I've never used that. For what I know, and for what I have observed in my models, and with the comparisons also with the hybrid simulations, which are both numerical and experimental. If you model the isolators just through these parameters used for nonlinear analysis without neglecting all the other parameters, the overall response is fair enough.
Okay, thank you. Thank you.
Okay, you're welcome. And just finally, we have to define the typology of analysis that we are going to consider. So the nonlinear time history analysis, we will have to select some ground motions. We will do it on Tuesday, sorry, next week, and before the numerical laboratory. And you see that this is the overall window for the definition of the time history analysis. I just highlight the typology of analysis. Analysis type we will consider nonlinear, and the solution type, this is what I mentioned before. The solution type we will choose a direct integration simply because we cannot say model because we will have a model which is nonlinear because actually we have nonlinear links for isolation devices. The model one is what I mentioned for linear systems, and you can actually perform the model analysis, and according to the model shapes and the model periods and frequencies and participating masses, the software can compute the nonlinear time history analysis quite faster, much faster. Because everything is already computed in terms of the deformation according to the vibration modes, and the software has just to compute the let's say the model coordinates as a function of time, which is much faster computation with respect to the direct integration for all the nodes and for all the degrees of freedom in the 3D space. And okay, you see here there are also what we were mentioning before, the geometrical nonlinearities parameters. You can account for P delta and P delta plus large displacements, but we don't want to consider them. There are also other issues which can consider also collapse, which allows you to remove at a certain time instant a certain frame element rather than a link, because maybe you are simulating a sort of collapse, and then after a certain time instant in your model, that element or those elements that you list here, they suddenly disappear, and you see what happens to the overall building. This is a progressive collapse analysis, actually. And then here we will have the load type acceleration, the load name U1. If okay, this U1 is back in agreement with the global system of coordinates. So this means that this is X. okay, the x direction. And the function, this is just a name that I've set in this model, and this is related to the ground motion that we have set. We have just to import some txt file, which is returned by databases of natural ground motions, rather than the simulation of artificial earthquakes with proper softwares. And then scale factor, you can set 9.81 if the ground motion is given in G's, rather than leave 1 if the values of the ground motion are already meter per second squared. And then you have to set also the number of output time steps. I generally and the output time step size. They could be different than the ones related to the input ground motions, but what I suggest is to exactly consider the same number of output time steps and the same output time step size, in order to have exactly the same resolution of results regarding also the input. Also, because maybe you can do some post-processing at the end by comparing the acceleration that is returned by the software to the initial input and so on. Then there is damping. Damping can be defined according to the Rayleigh formulation, stiffness proportional rather than mass proportional, or both together according to Rayleigh. The time integration, generally this method, the Hilbert, Hughes, Taylor, is the most proper one, and then okay, nonlinear parameters can be just left like that. The load case, okay, this is no time history. Here there is linear, non-linear, static, non-linear dynamic, which is the time history. There is also response spectrum and so on. An important aspect could be the following. You see here initial conditions. Okay, this is important because actually for rubber bearings, for instance, we start from 0 initial conditions. Okay, because and also for lead rubber bearings, simply because they are just links. They are just represented by links which provide the fair behavior of the hysteretic response. What we have to consider here, and this is what I've reported in this figure, is to continue from state at end of nonlinear case, and you see gravity. And actually, this is important when we have curved surface sliders, because we want to keep also during the analysis, the horizontal analysis, the dependency of the lateral response of the isolators with respect to the vertical loads. And this is how to apply the gravity. So you just select all the external loads which are applied to the building, or generally to the structure, and then you apply them within this gravity, which is the name that I've chosen for another time history nonlinear analysis, which is according to this time history. So this time signal, which is just a ramp and then a constant value. And the ramp, you see that assumes value equal to 1. And this is just a multiplication factor for gravity loads which are used within the software and within the analysis, the time history analysis of the horizontal earthquake. And you see that in order not to apply these gravity loads in a too fast way, so that then you may have oscillations, vertical oscillation at all the structure points. We have just set this ramp time equal to 10 seconds and then other 5 seconds by keeping constant the final value. Okay, so what we have observed in our models is that 10 seconds of ramp is long duration enough to provide a statically application of the gravity loads with no additional fluctuations of the internal forces. So once you have performed this, and then you say, okay, the earthquake will start at the stated end of this gravity nonlinear case. So that all the links which represent the behavior of the curved surface sliders have actually the proper vertical load, and from that instant to the end actually of the earthquake simulation, there will be also the variation of the horizontal response with respect to the vertical force, stepwise applied to the links. So this is it for the modeling strategies within SAP 2000. Is there any questions for what we have observed?
I have a few more questions.
Yes.
The first one is related to the damping and which formulation, which model of damping should we use?
Yes.
Is it better to use the Rayleigh damping, mass damping, and also the, I don't know if you can say more about the damping.
Yeah.
And if, for instance, if we were going to use the Rayleigh damping, which one are the periods of interest that we should assume as boundaries, let's say, the two fundamental periods? This is the first question. Thank you.
Yeah. Okay, so depending on the damping assumptions, okay, we have different hypotheses that we can be applied to all to our models. Okay, there could be mass proportional, stiffness proportional, or Rayleigh damping generally for both of them. So both stiffness and mass proportional. We have to keep in mind that we are actually modeling an isolated structure. Okay, so this means that with the proper nonlinear behavior of devices, we are accounting for hysteretic damping, which is provided by the isolators. Okay, and so consequently, the effect of damping is already provided by the largest amount of damping. I mean, the most important one is already provided by the isolation devices. This means that if we account for also for other additional damping related to the overall superstructure, this may affect also the isolation system, and maybe we are over damping the overall model, and we are underestimating displacements and consequently also internal forces. So what is generally done for seismically isolated structure is not to consider additional damping, since there is damping within this hysteretic damping for nonlinear devices, rather than also for rubber bearings, which are linear devices. There is a linear damping, constant damping with the equivalent viscous damping ratio assumed in design. If we want to consider also an additional damping, it should be limited up to 2% for 2 to 5% maximum for seismically isolated structures. And generally, I think that Rayleigh damping could be fair enough, rather than stiffness proportional. Maybe is much more conservative, but we have also performed some computations with Rayleigh damping by considering from 2 to 5% of damping ratios. And regarding the other question about which kind of periods to consider for the definition of the Rayleigh damping, okay, we know the drawing for the damping ratio with respect to the angular frequency. It is something like this. Okay, and we want to consider an average, let's say the 2% damping, let's consider, for a set of angular frequencies which consider at least all the frequencies that we can have. let's keep in mind that frequencies are just related generally to model analysis, and model analysis can be computed whenever we have a linear elastic model. In these cases, we are exception made for rubber bearings. For the other two typologies, we have no linear behaviors. But in any case, we can consider a very wide range of angular frequencies, so that at least maximum value of 2% will be considered. But it could be also lower, okay, because this is the behavior of Rayleigh formulation, okay. So this is generally we don't account for additional damping just for seismically isolated structure, because there is already the hysteretic damping provided by the devices. If we do have, it is mandatory to consider additional damping. It should be limited to 2%, maximum 5%, and according to the Rayleigh formulation, with a very wide range of angular frequency. We should include the design angular frequency, what I called actually omega isolation, and also all the higher modes for the mostly related to the fixed bay configuration of the building.
Thank you. Now it is clear. And the second question is related to the still about the non-linearity, and particularly for the P-Delta effect. How we can account for these effects due to the type of isolator that we are going to install. For instance, when we have friction pendulum devices, we could have two surface, for instance, with the double surfaces, with two surfaces, we have P-Delta effects that are transmitted both to the superstructure and let's say foundation.
Yeah.
What you can say more about this? Is it important to account for this the effects associated to the let's say this non-linearity or not?
Okay, generally, so how about how to model them? There is just here you see the geometric nonlinearity parameters. You just account just for P delta rather than P delta plus large displacements. Obviously, and consequently, we will have the probability to not to achieve a convergence is much higher whenever we account for P delta rather than P delta and large displacements at the formation. So as we increase the complexity of the overall model, we also increase the probability of non-convergence. Okay, so maybe we can at least try to do that. I would say that for general applications for buildings, for instance, where we have rather small displacements, for ordinary applications, the P delta effects induced by the isolation devices can also be neglected, just because the foundation, the substructure, the foundation structures, and the columns, for instance, should be much stiff and robust to not to have particular influence induced by the P delta effects, and the same for the interface between the superstructure and the isolation layer. So maybe something happens when we consider bridges, because the axial load induced by the deck are huge values. Automatically, we have also large sections also for piers. But maybe that is depending on the static scheme of the piers and of the general structural system of the pier and of the deck. That could be the case where this could be it would be worthy to consider.
Okay, but thank you. But I was thinking probably my question was related to the specific properties of isolators. In this case, maybe if we can go some slide back where you were presenting about friction pendulum, the properties of the device.
Yes, this one.
No, but here it is not present. No, because I was thinking how we can, if we want to account for the pedal effects that are transmitted by the device to the superstructure,
yeah,
how we should account for this, for the, let's say, this additional force related to the displacement, of course, of the isolator. And
yeah, you mean
we can consider this,
yeah.
I don't know, as a couple of bending moments, as I don't know, an additional shear couple. What's the difference? I don't know, or what the best way, the more efficient also to account for this effect.
Yeah, you mean this slide where there was the comparison between the single curvature installation, which is this one.
Yes.
Okay, and then this is the plate, and then there was the other one with exactly the opposite. Okay, so we have the hinge below, and here we have the main sliding surface. Okay, so here we have actually the vertical force, which is actually aligned with respect to the hinge, so it will not change the it will not change the position with respect to the top plate, but in the second case, it will not change the position with respect to the foundation, to the substructure, and it will represent the P delta effect on the superstructure. So yeah, I see your point, but I think that this is quite actually quite difficult to model, to be modeled. I mean, dynamically. What we can do is actually to consider just the fastest analysis that we can have from the time history point of view. So without accounting for the actually for the P delta effects. Once we have computed this, we can check the maximum displacement during the time series of displacements at the isolation level, and then we can just apply the vertical force times the maximum displacement of the isolator, either to the substructure for the first solution, rather than to the superstructure to the second solution, as a constant value of additional moment, rather than actually to apply the force at a certain location in order to consider the proper internal stresses and forces induced by that additional force and location. And this could be also done by looking at the time instant where we have maximum displacement, and by looking at that, we can do actually a combination for a given time instant by adding some other load pattern. So we can define a load pattern by considering the new location related to the maximum displacement, and to sum up the internal forces related to the time instant where we achieve actually the maximum displacement. That could be a strategy.
Okay, but this, thank you. But this kind of force is a force or a bending moment that we should apply on the, for instance, superstructure. I don't know which kind.
Okay, actually, that should be a couple, because we have to move the effect, because we will surely have the application of the vertical load at the same location, because we have the link there. Okay, so we should add an additional couple in order to obtain at the end of all the end actually of end computations the location of the vertical reaction displaced with respect to the maximum displacement that we have computed.
Okay, thank you so much.
You're welcome. Other questions?
Sorry, tomorrow we are going to apply the model in SAP. What we learned today.
Not tomorrow, but we will define the case study structure on Monday.
Okay,
and
perfect.
Tomorrow we will see together the fast rules for designing the isolation systems according to rubber bearings, lead rubber bearings, and curved surface sliders. I will share with you within our shared folder as I said, the research article that I have authored about these procedures, so that you will have. I also deliver the presentation for tomorrow, but you will have also a research article which actually summarizes all these procedures, and then we will apply those procedures because my aim is to let you face the design procedure for these three typologies of isolators. For a given structure, it will be a very easy structure. We will consider a 3-story structure, very regular. And once we will compute the overall, we will guess sections, but once we will compute the overall mass of the structure, we will try to define the isolation layers. And then on the laboratory, on Wednesday, we will perform a nonlinear time history analysis with the software. And on Tuesday, we will select, we will proceed with the selection of the seismic events for nonlinear time history analysis. And then finally, we will compare the response which is returned by the software by considering the finite element model, the full model of the building, by very simple responses returned by single degree of freedom oscillators. And we will see how much this simplification of a base isolated structure is useful just for a get started estimation of the overall performance of the isolation systems. And then we will draw conclusions on Friday, which is the last day of the short course. I just want to remind the same that I've said for MATLAB. If you need if you don't have actually SAP 2000 and you need to use a computer of the faculty, just let me know. I have the connection link for remote desktop, and you will be able to use actually the software. So just email me by saying that you need the access to the computer of my faculty, and I will allow you to use the software that we have installed here. Okay. I think we are done, and so let's see tomorrow for the actually the definition of the design procedure. Have a nice day.
Thank you. Bye.
Bye bye.
Thank you, Professor. Have a nice day.
Bye bye.